All right, today we're putting on our detective hats. We're going deep, deep underground to solve a mystery that's literally written in stone and pressure. We're going to map a world we can't even see.
I mean, think about it. That's the real challenge here, right? Thousands of feet below us, there are these huge, incredibly complex rock formations holding the energy resources we rely on. We can't just pop down there and take a look around. So, how in the world do you draw a map of an invisible place? Okay, so first things first, let's get a handle on our crime scene. It's called a heterogeneous reservoir. Yeah, I know, it sounds super technical, but all it really means is that the rock isn't the same everywhere. It's more like a patchwork of different zones, which makes figuring out how oil is going to flow incredibly tricky. And to really get a picture of this in your head, just forget the idea of some simple underground pool of oil, like a giant uniform sponge. That's just not how it works. A much, much better way to think about it is like cracked concrete with all these little pathways and dead ends, or maybe even a complex multi-layered cake. That's the kind of complexity we have to map. So if we can't see it, how do we investigate? Well, we listen. We listen very, very carefully. Turns out the only voice we can hear from that deep underground is the story that pressure tells us. By watching exactly how pressure changes when we start producing from a well, we can start to build our map. And you know what? This story, it's got a classic three-act structure. Act 1, the fissure flow. This is where oil shoots through the biggest, easiest pathways, the superhighways of the rock. Act 2, the transition. This is where the tighter rock, the matrix, starts to slowly feed its oil into those pathways. And finally, Act 3, the total system flow, where everything stabilizes and the whole area starts acting like one big connected unit. But here's the thing, the clues in that story, they can be super subtle. So how do we spot them? We use a really cool analytical tool called the pressure derivative. Honestly, the best way to think about it is like our detective's magnifying glass. It doesn't just look at the pressure, it looks at the rate of change of the pressure. And that amplifies all the tiny shifts, revealing the hidden patterns in the rock. Okay, so with our magnifying glass in hand, we can start to figure out what kind of reservoir we're looking at. And our number one suspect, the most common one we run into, is what's called a naturally fractured system. The technical blueprint for this is called the dual porosity model, but the idea behind it is actually pretty simple. You've basically got a reservoir with two distinct parts. There's the dense rock, we call that the matrix, which is where almost all of the oil is stored. And then you have this network of cracks, or fissures, that act like highways for that oil to get to our well. So what you've got here is this fundamental trade-off. The matrix is like the vault. It's got tons of storage, but terrible flow. The fissures are the highway. They have almost zero storage, but fantastic flow. And the whole game really is figuring out how to get the oil out of the vault and onto that highway. To crack this code, we're looking for two key clues, two parameters in the data. The first is called omega. It answers the question, how much of the oil is in the cracks versus how much is in the rock? And that controls the depth of a signature dip we see in our data. The second is lambda. It tells us how easily can the oil move from the rock into those cracks, and that controls the timing of when that dip happens. So what is this signature clue I keep talking about? Well, it's a very distinct dip in our data. See, the fissures produce their oil really fast, so their pressure drops quickly. Then there's a pause, a dip, as those fissures basically wait for the slow-moving matrix to start resupplying them. That dip, that is the absolute smoking gun for a dual porosity system. No doubt about it. Now, this whole story can actually play out in two slightly different ways, two flavors, if you will. The first is called pseudo-steady state, or PSS. This model assumes the rock blocks empty out all at once, and that gives us a really sharp V-shaped dip in the data. The other is transient flow, which assumes the blocks empty gradually from the outside in. This gives us this more gradual U-shaped dip. The shape of the clue tells us exactly how the matrix is feeding those fissures. But wait, a fractured system isn't the only possible culprit here. Sometimes our detective work points to other suspects, like distinct layers of rock or some really sharp geological boundaries. We could, for example, be looking at what's called a double permeability system. This is that layer cake model we mentioned earlier. You've got at least two different rock layers, both producing directly to the well, but they're also able to feed each other if the pressure changes. Or maybe, just maybe, it's a radial composite model. And honestly, the easiest way to picture this one is a donut. You've got an inner circle of rock around the well with one set of properties, and then an outer ring of rock with a completely different set. The clue for this one, oh, it's unmistakable. As the pressure wave from our well expands outward, the very moment it crosses that boundary from the inner zone to the outer zone, our data shows a sudden step, either up or down. That little step is a huge signal telling us, hey, we've just crossed into a totally new geological neighborhood.
And there's a really simple, almost catchy rule of thumb for this model. Down equals good. If that data steps down, it means the pressure wave has moved into a region with better flow, higher permeability. It's an incredibly powerful clue for us.
Okay, but what if that boundary isn't a neat circle? What if it's a straight line? Well, that's a linear composite model. This usually points to a major geological feature, like a fault line. It's kind of like you're walking along a nice sandy beach, and then boom, you smack right into a wall of solid rock. And this model, this one can give us one of the most dramatic clues of all. If that pressure wave hits a complete barrier that it cannot cross, what's called a ceiling fault, the signal in our data, it literally doubles. It just shoots up. I mean, you can't get a clearer sign than that. It's basically shouting, stop, the reservoir ends right here. Okay, so we've looked at fractures, layers, boundaries, the whole lineup of suspects. But let's take a step back. Why does any of this matter? Why is getting the right blueprint so important?
Because getting the right diagnosis, it changes absolutely everything. Remember that ceiling fault, that big wall? Well, identifying it means you don't waste millions drilling a dry hole on the other side. Knowing you have a radial composite system and seeing that down is good signal tells you exactly where you should drill next to get the best results. It all leads to more efficient recovery, safer operations, and much, much smarter investment.
So really, the whole point, the big takeaway here is this. All of this detective work is about deeply understanding the natural system we're working with. When we have the right blueprint, it means we can work with the reservoir's natural system instead of just fighting against it. This pressure story is really just one of the many languages the Earth speaks. The entire history of our planet is written in the rocks right beneath our feet. It just makes you wonder, what other secrets are written in the rocks down there, just waiting for us to learn how to read them?